Hello everyone, welcome to Unit 6. This week we're going to be talking about randomization, which has obviously come up a number of times over the course of the module thus far. We've talked already about why randomization is important, and we're going to talk a little bit more about it. But most importantly for this lecture is we're going to talk about how to randomize patients. And essentially when we're making decisions on how to randomize patients in a trial, we're trying to balance two important and competing concerns. And those are the allocation concealment and the efficiency of the trial. And so by allocation concealment, I mean that we're not able to guess what the next treatment is going to be for the next patient enrolled in the trial. And our concern there is to prevent bias. And what I mean by efficiency is that our estimates are as precise as they can be for a given sample size, or we can detect smaller effects for a given sample size. So efficiency is about the statistical efficiency of the trial, extracting as much information as possible from the trial we have in front of us. And so in addition to describing how different randomization plans balance these two issues, we'll also talk about very practical concerns about the randomization that you'll need to be aware of. So we know from the beginning of the module that randomization in the use of experiments in clinical trials is often credited to Fisher. And again, Fisher's main concern at the time was about the statistical properties of the analysis. However, the use of randomization precedes Fisher, and there are historical examples, and you can go to the Jameson Library and you can see all kinds of historical examples of people using this idea of randomization in order to get at answers to causal questions. And so here we have an example from 1648. You have two people, they're trying to figure out whether they're going to do bloodletting or something else, and they're just going to randomly distribute the two groups of patients and do what they do, and then see who dies the most. Kind of grim. But this idea of randomization is an old idea for sure. In the context of clinical trials, though, randomization was probably best formalized by Bradford Hill in this very famous trial about tuberculosis published in the BMJ. So this is recognized as one of the very first randomized controlled trials, and this is really what cemented it as a tool for causal inference. And to use Bradford Hill's terms, he viewed randomization as a way to avoid, quote, personal idiosyncrasies or personal judgment. So in other words, without randomization, patients were appearing to come onto a study or a trial. The physician or the clinician would make some decision based on the characteristics of that patient, whether they would get treated or get a new treatment or get the old treatment or whatever. And that was biasing the studies, because maybe the healthier people would be given the experimental treatment. Maybe the sicker people would be given the experimental treatment, depending on what kind of trial it was. And so the whole point from Bradford Hill's perspective for using randomization was to remove that personal judgment, the personal idiosyncrasies out of the decision of who gets the actual treatment. And of course, we discussed how we can use DAGs, directed acyclic graphs, to support this intuition. And the idea being that we can look at an effect between X and Y, and we can assume it's unconfounded in a randomized controlled trial because we've randomized X. We've randomized the allocation. And so since there is no causes of the allocation, it's random, there can't be any unblocked backdoor paths between X and Y. And so when we talk about randomization to that point, it was for this purpose, this idea that we were going to have a comparison that is unconfounded at randomization. But we also have to be concerned about what happens post-randomization. And so in order to do that, though, we need some additional steps. It's not enough to randomize. We have to make sure that the allocation is concealed. In other words, it's not enough to use some kind of a device to randomly assign patients. We also have to make sure that the clinicians or the people involved in the study don't know what those allocations actually are. And so Vickers tells us there's two fundamental characterizations we have to have in order to have allocation concealment. And so the first one is that we can't be able to predict the group to which a patient will be randomized until after that patient is unambiguously registered onto the study. And what we mean by this is it can't be a situation where you are consenting people, you enroll them in the trial, you get their random allocation, you see what it is, and then you decide to unenroll them from the trial because you didn't like the randomized allocation. So this has to be a system is what we're talking about, where we can't know what the allocation is until the people are unambiguously registered on the study and cannot just be taken off without some kind of evidence of that happening. And then the next thing is the system has to ensure that we can't change the patient allocation. All right, so we have some kind of a device, which we'll talk about, to randomize patient, and then we have the system to maintain allocation concealment. So how do we do that? So the kind of stereotypical way of doing this is to use envelopes. This idea that we have numbered envelopes, and inside each envelope, wrapped in a piece of foil, is an allocation. And so that a patient comes into the clinic or wherever the study is being done, the person who's doing the consenting and the screening goes through all the criteria, and they are consented and enrolled onto the trial, at which point the person who's doing that work goes and gets the allocation list of envelopes, or the stack of envelopes. They take the one off the top and they open it up, and that has the allocation. But really, if we're thinking about this idea of allocation concealment the way Vickers described it, this idea that we can't know the allocation until they're unambiguously enrolled in the trial and that the allocation cannot be changed, you kind of have to think about what you would really need to do in order to maintain real allocation concealment if you were using envelopes. So let me just provide as kind of a scenario what you might consider. You could have tamper-proof envelopes, first of all. They could be opaque so that you can't sneak and see through with a bright light. You could have signatures over the seals, maintain the fact that they haven't been tampered with. You have a patient who's come into the clinical trial, and you record their screening criteria. And you might have a few other pieces of information about the person, like their age or their sex or some other kind of not identifying characteristics, but things that are specific enough to that person that within the context of your trial, you'd be able to link that to the actual person. You could write those things on the outside of the envelope prior to opening it to ensure that you had some kind of proof the person was, unambiguously enrolled on the trial. And then you could open the envelope and include the allocation information in what you were doing. That's something along the lines of what it would take. So in practice, what we always recommend is that people use some kind of a system of electronic databases to manage this. And so this is a quote from Vickers from one of the assigned readings. And he's making this scathing critique here that he's had people complain about using electronic databases as though or some kind of a specialized technology. And this is in 2006. And he's bemoaning the fact that, if we're still considering computers to be a specialized technology, then, we're in a bit of trouble. And, it's even more true, of course, today. So really, in my opinion, there's no reason that we shouldn't be able to make sure everybody is set up on an electronic database. And essentially the idea would be is that you have two databases, one of which has the allocation and one of which doesn't. And the second one is password protected. And so you enter in information into a database, you click on a button to randomize, you get the allocation from the randomization list, which is separate. That gets entered into the patient spreadsheet. That can't be changed once you've done it. Everything is recorded, everything is logged. Nobody could go back in time and alter that information without being, found out. And so whether you need to invest in some kind of a programming resource or you need to just buy access to a commercial kit, one of those two things for the vast majority of trials that are answering questions worth answering should be taking that approach. And so you can use these services. They're actually quite competitively priced these days. So sealed envelopes is a very popular one. They have a patient electronic case report form that comes with it. If you want to use that, use that. And the prices have come way down for these things. So it's no longer a massive financial barrier. If we think about existing clinical trials units. I was speaking to clinical trials unit director in the UK, and they said that programmers were their largest staff group. So there's lots of money in programmers to help kind of work these systems out for themselves. So this issue of allocation concealment is a really important one, and it's something that if you're going to take your trial seriously, it's one of the areas where you really have to invest in a little bit to do that. And so I keep talking about people like, sneaking peeks into envelopes and everything else. The issue with allocation concealment, it's not just that I don't think personally that clinical investigators are out to cheat, or trick people or anything like that. But we have to understand that people have unconscious biases that they're not aware of. I have them, you have them, everybody has them. We also know there are incentives for investigators to be in research, to be involved. For a lot of clinical investigators, being a researcher, is a path to promotion. And we know that if you're doing research, we know there are incentives to find effects. And that when we conduct trials, we're usually conducting trials of things that we hope will work because we're trying to help people, right? So your career incentivized to find positive effects because that makes it easier to publish, which is not how it should be, but it is how it is. And we want to find positive effects because we want to help people. And unfortunately, there are very few disincentives to either sloppy research, which I think is not uncommon, or even dishonesty, which I assume is pretty rare. But even when people get caught out for sloppy research practices, there aren't really severe penalties for that, right? So what I'm getting at here is that there's kind of this recipe for people and their unconscious biases to sometimes do the wrong thing. And importantly, even just the possibility of that is what someone else, some other stakeholder, some other person who's interested in the result of the trial, some other stakeholder can point to that situation and then call your result into question if you haven't taken painstaking means to ensure that you had an allocation concealment system that holds up to scrutiny. And so if some person came along and said, well, I don't trust the results of this trial, maybe they prefer a different kind of treatment, who knows, whatever. There's a lot of money at stake sometimes in these things. Someone could say, I don't trust the results of that trial. I don't see how the allocation concealment was maintained. Well, that can plant the seed of doubt, in other people's mind. And ultimately, as we've talked about before, you need other people to trust the result of your trial. You need people to trust you, a stranger, that you've done a good job and you've minimized the risk of bias in your study so they can believe your result. And so this idea of setting up a impregnable system of allocation concealment is a really important one. Okay, so that's allocation concealment and a little bit more about why we do that. The kind of technical bits are, think about here, we're going to talk about the different types of randomization. And essentially we have 4, and we're going to talk about 3 of them today, and then outcome adaptive we'll talk about in the next module. So we have what we call complete randomization, restricted randomization, then covariate adaptive. And we'll just kind of build through these, and as we'll do it, we'll see this trade-off between efficiency and allocation concealment. And so if I completely randomize people, which means that as each patient appears in the trial, I flip a coin or have the computer flip a coin for me, and that there's no relationship between the outcome of that coin flip as we go from one patient to the next, I will get perfect allocation concealment. There's no way for you to systematically predict what the next coin flip will be. If I tell you heads or tails and I flip the coin, you will guess. Sometimes you will be wrong. Sometimes you will be right. That will happen 50% of the time over a long series of guesses. But there's no systematic way for you to beat the 50-50. Right? You can get lucky for small stretches, but that's it. So that's complete randomization. It gets you perfect allocation concealment. And I've just made this hard-pressed case for why allocation concealment is so incredibly important. But complete randomization brings a problem. And the problem is that you get a risk of unequal sample sizes in each arm. So let's say that you've got a 2-arm trial, like we've been discussing throughout this module. You're flipping coins as patients are enrolled in the trial, and you could just get a string of heads at some point. So you wind up with 20 patients in one arm and 24 patients in another. And the problem with that is that the analyses of trial data, they're more efficient when we get an equal number of participants in each treatment group. All right, and so if we're looking at something like a continuously distributed variable, our measurement of the average treatment effect would be a difference in means between the two groups. And then generally when we look at power for a study like that, which we'll talk about a lot more in 2 more modules, it's a function of the sample size and how it gets split out between the two groups. What we wind up with is that power is usually maximized for when the sample sizes are equal in each of the two groups. And this is a real concern because patients are precious from a life standpoint, but also from the standpoint of a study design. We want to use the information that we get from our patients. We want to get the most out of it. We want to learn the most. We have people who are sacrificing autonomy and being exposed to ununderstood risks. And so we want to get the most possible information out of the trial as we possibly can. And the one way to do that is we have an equal number of people in each of the two arms. Now, that being said, this concern about unequal allocation, there are matters of degree. And so what I mean by that, if we look at this plot, what we have here is the sample fraction, right? So this is the fraction of the total sample that winds up in one of the two groups. And so over here on the x-axis to the left, we have 0.5. So this is our best case scenario where you get half in each group. And as we come over here, this imbalance in the allocation gets worse and worse and worse and worse. And then we have a number of power curves. All right, so this is power at 0.5. So this is if there's an effect, that's the size that we nominated at the beginning, there's a 50-50 chance we'll detect it, and up to a certainty. All right, so what happens here? So we start off in the perfect situation here. So if I start off in a study with power of 0.8, which is a pretty common number to design the study around, this is if my imbalance increases and increases. And what you see here is actually pretty flat. Right? There's not a huge dip in power, even when we get out to an imbalance, of 0.7. Right? 70% of the observations fall in one group compared to the other. Right? And then it starts to dip off more out here. So the point I'm trying to make here is that the imbalance thing is real. We want to take it serious, but it takes kind of substantial imbalances to really have a substantial impact on your trial. And so what's the way to fix this? Well, like everything else in a trial, usually the best thing to do is just to have more patients recruited when we can. Right? So this is if I'm looking at a probability that my allocation winds up at a 50%, which is what I want. And this is just the binomial distribution. We looked at this once earlier in the module. If I was to do a probability mass function for binomial distribution where n equals 6, what does this tell me? Well, this says that most of the time, here in this top left one, most of the time I'd get a 50-50 split, but a not insignificant number of times I'd get something like 40-60 and so on. So here my distribution is fairly wide, and it's not at all unusual to get imbalances that aren't 50-50 with n equals 6. The same for n equals 12. It's a little bit more peaked here in the middle, and extreme imbalances are becoming more rare. That becomes even more true. You can compare this one to the one above it. This distribution is much narrower now when we have n equals 24 compared to when it was n equals 6. The vast majority of randomizations here are grouped around 0.5, which is what we want. And once I get out to n out of 100, n equals 100, then it's be very unusual to get the kind of imbalances that we were talking about before that would actually substantially affect the trial. And so the point here is that this issue of imbalance in allocation is really a problem for small trials, and is pretty negligible for any kind of a decent sized trial. Once you get into 60, 70, 80, and 100 patients and beyond, then the issue pretty much goes away. It would be very, very unusual. All right, so what is the solution to this? And the solution is that we're going to use some form of the restricted randomization, which I said that was the other. So we had complete randomization, and then we have restricted randomization. And that just means that the number of possible allocation sequences is somehow constrained so that we get a treatment balance in the trial. All right, so here's an example. We could just do what's called a random allocation rule. And what that would mean is that you choose from a set of random sequences that guarantees that the two things are equal. N in group 1 is equal to N in group 2. And so we can actually do this. You can use the computer. If you have 10 people coming onto a trial, they can go into one of two possible groups. You can calculate the number of possible, sequences that you could generate. And then you would choose the ones out of that group where it's 5 and 5. All right, so you could have some sequences that are 0 in one group and 10 in the other. You get others where you get, 6 in one and 4 in the other, so on and so forth. We just take the ones where it's 5 and 5, and we use those in our trial. So now, unfortunately, the problem is that we've raised the risk of there being some kind of a selection bias or a break in the allocation concealment. And what I mean by that is that if you know that at the end of the trial you have to have the same number in each group, then if at any given point in the trial, if I know that I'm out of balance, I know that at that particular time, say I've got 13 in one group and 7 in the other, then I know that the next patient that comes in, it's actually more likely they're going to be assigned to control, because I know those two numbers have to be equal towards the end of the trial. So I've made it possible to guess, and my guessing might not be very accurate, but it'd be better than the 50-50 I had before. All right, so now we've traded off something, right? Before we had complete randomization and perfect allocation concealment, and by making this restricted allocation rule, using a random allocation rule, now I've raised the problem that we might get a break in allocation concealment. However, I know that treatments will be balanced with full recruitment, but with this particular scheme, it doesn't necessarily guarantee that they'll be balanced in the interim. So you could still have strings of, lots of active arm allocations. So you have imbalances during the trial, but at the end, they're going to be balanced. And so that's important to think about because often trials don't recruit fully. So instead, what people usually do is they use what are called random blocks. And this would be by far, I think, the most common way of randomizing patients. And what we do is we divide the patients into small groups. We call those blocks. And within each of these blocks, we use a random allocation rule, which is to say that we have an equal N in each group within each block. All right, so at the bottom here are a couple examples. We could have blocks of size 2. In each block of size 2, then I'd have to have 1A and 1B. And it could be one of two possible combinations, AB or BA. Here we have blocks of 4, and then these are the different possibilities we have there. All right, so this is a way that, as the trial went through, maintain balance at the end of each block. So we don't have to get to the end of the entire trial. And maybe you get to the end and one block gets cut off, but that's not going to cause a real problem. Having an allocation off by 1 or 2 patients, as we've seen, really isn't that big of a deal. But again, we still have this issue. There's still a risk of selection bias. And so you have to think about how easy it is to guess the next allocation. And so here, this is completely random. I go A, B, B, A, B, whatever this is. You really don't know what's going to come next. You can guess, and you'll be right 50% of the time, but that's it. Here, obviously, if I do blocks of size 2, A, B, BA, blah, 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 well, then here, what's my next allocation? Well, you know it's going to be B. If I do blocks of size 4, I come through, what's my next allocation going to be? Well, it's going to be B here. Now, this is another purpose of blinding, helps with this, obviously. If we don't know what comes next, if we don't know what people have had before, then we can't possibly guess either, right? But you need allocation concealment for blinding. So if I have another example here, ABB, and here you might not be able to guess exactly what patient gets what, but if you understood that this was A, B, and B, then there are going to be 2 A's here. So the next patient who comes in and gets enrolled is going to be a higher chance of getting the treatment A than B. And you might use that information, theoretically. Or someone might accuse you of wanting to use that information, which is probably the more important threat. All right, so anyway, when we use this kind of restricted, we use a block randomization, there is this possibility of losing allocation concealment and being able to at least theoretically guess the next assignment. So in general, this risk is greater than that it would be for the random allocation rule. The random allocation rule, at any given point in the trial, you have so many allocations remaining in the study. If you know how many you have in each arm up to that point, then you know how many you have to get to. So it says something about the probability of the allocation coming up. But it's still not going to be quite as clear as if you knew what was coming up within a block because it's a smaller group size. And as we saw, this risk of selection bias or breaking allocation concealment, it gets higher with smaller block size. And so what we do is we use a random block allocation where we use random block sizes, and that we don't share that information with anyone. It's a part of how we produce the randomization list, and it's described at the end of the study, but nobody knows during. So we might have a situation where we use block sizes of 2, 4, and 8. And so you don't know if you see an A and a B. You don't know if you just completed a block of size 2 or if you just started a block of size 8. And so that kind of helps solve that problem. And so when we use the random blocks, then treatment imbalance is impossible under full recruitment. If recruitment falls short, the random blocks will keep the imbalance relatively small throughout the trial. And like everything else, a small trial is problematic because it'll force the use of small blocks. And so you have less flexibility in terms of making random block sizes that are bigger than, say, 2 or 4. So to that point, that's just trying to keep the trial as efficient as possible to try to make sure that we have an equal allocation of treatments across our study, the same number of patients in both arms, as close as we can get to that. And so now we have to come back to this issue of covariate imbalance, which we discussed in the last module, which is the great boogeyman of clinical trials. The whole point of randomization is that we're trying to compare like with like. We're trying to get two similar groups, and so that when we see a difference between them, if we do, we can attribute that to the effect of our treatment. And as we've said repeatedly, but this is one of the biggest misconceptions in trials, is that randomization is about exchangeability of treatment groups with respect to the outcome, and that that's only true in expectation. And what I mean by expectation is that over the long run of a series of hypothetical trials, that we would tend to get the true answer as the average of all of those hypothetical trials. Now, it's valid estimates, and by that we mean it's unconfounded. But again, we still have to deal with the trial in front of us. We only have one trial, and there's no guarantee that our groups are exchangeable. And so people place their concerns about this lack of exchangeability, the idea that the two groups won't have the same distribution of baseline risk, and they start to attribute that to concerns about covariate imbalances. And we went into this in quite a bit of detail in the last module, where we shouldn't be that worried about we shouldn't be that worried about covariate imbalances only to the degree that covariates help us predict and understand variation in the outcome. And of course, in every trial paper, there will be these kinds of tables, which we talked about before, and sometimes they have p-values, and we made arguments about why those aren't super useful. But we do want to understand this stuff because we do want to be able to pick out the strong prognostic factors before the study begins so that we can adjust for those things in a statistical model and reduce the variability of our outcome. So if our outcome, if it's blood pressure or forced expiratory volume or whatever it is, that will have predictors that help explain why some people have a high value and why other people have a low value. And we can use statistical models, which we'll see in the next module, but we touched on it a little bit in the last one. We can use statistical models to adjust for those things. And when we do that, the variability of our estimators can become more narrow. We remove variability. And the more narrow these things become, these distributions of our estimators, the more precise of an estimate of the treatment effect we can get. And so covariate imbalance is dealt with, again, by adjusting for things in a statistical model. Following from this kind of concern about covariate imbalance that people have, they then start to view stratification as the cure. And what we mean by stratification is that you take something you think you really want to be balanced between the two groups. If you're concerned about covariate balance, or we take some prognostic factor like sex, create a randomization list that's restricted within each sex, and that makes sure that we have an equal number of allocations to treatment and control within each of the sexes. And so that, in the minds of some people, presumably cures the imbalance problem. We've artificially balanced the data set. The only issue with that is we still have to do the adjustment in the statistical model, which I said we should be doing anyway. In other words, when we have a strong prognostic factor that we want to account for, and I'm telling you that you have to adjust for it in your statistical model, then we're going to go out and stratify. And if we stratify on that variable, we have to adjust for it in our statistical model anyway. At the point of stratification isn't to deal with the imbalance per se, but that when I'm going to adjust for a covariate, if the treatment allocation is balanced within strata of that covariate, then I get the most efficient estimate. In other words, stratification and adjustment work together to give us the best, most efficient estimate of our treatment effect. So the practical outcome is the same. We are going to stratify on strong prognostic factors when we can, but that's not a complete solution. You still need to adjust for them in the model. Now we have problems with stratification, and that is that you can only really stratify for a small handful of things. If we stratify, for 5 or 6 or 7 things, then you can think about patients falling into individual little cells defined by all those combinations, and you might have cells that don't have any observations whatsoever. It becomes untenable to stratify. So you can only stratify for a couple of prognostic indicators. And it's never entirely clear how to deal with continuous covariates, and continuous covariates are the things that are most likely to help us get gains in efficiency, because continuous variables contain more information than categorical ones. There's more to be learned by using them. And so we have things that we call covariate adaptive designs, and people are trying to deal with this issue. And so you could have a situation like this. This is called minimization, where let's say we have 1, 2, 3, 4 different variables that we're concerned about, and then we can chop them up into low, medium, and high. And so each patient then characterized by their values on these 4 different variables. What I can do is I can create a table where I have each of the treatments in the trial, and I can keep track of what combination of factors the patients that have gone into each of those treatments have. And then what I do is when it comes up to the next patient with a certain set of characteristics, I can just put them into that treatment. Now, minimization isn't without certain critiques, and Stevenson goes through some of those in the reading. But one of the biggest ones that it comes up with, especially for smaller and academic-led trials, is that minimization requires some fancy programming to make it happen, because you can't produce the randomization list in advance. We'll talk about this in just a minute. You have to have a computer system set up that can input the information about the covariates in the patients, do a calculation, and then give you that answer back. So in practical terms, minimization can be quite a technical challenge to achieve. It's not insurmountable, but if you're going to do a small trial in your clinic or whatever, it's often not much of an option. And the gains you get aren't necessarily going to be very astounding. And so what we would generally recommend as a basic strategy, the hard work is in identifying the strong prognostic factors before the trial begins. This is where your expertise has to come to the forefront. If you know what you're doing, you understand your outcomes, then you should be able to understand what the strong prognostic factors for those outcomes are. And we know in advance to go ahead and collect that information so we can adjust statistical models for those. That's the hard part. So you're going to identify the strong prognostic factors. You stratify on 2 or 3 of the most important of those. Use block randomization with random block sizes. And then when it comes to the analysis, you adjust for all of those factors, and whether they were stratified on or not. Right? You're trying to stratify on your most important ones to improve the efficiency, but it's not an excuse to not adjust for the things you couldn't stratify on. You still go ahead and do that. 95 trials out of 100 would be best served by this kind of simple strategy. It does everything you need just about as well as you can do it with a minimal amount of kind of technical know-how. So finally, just to discuss some of the practical issues, and probably the most practical issue about how to do randomization is this idea, which Stevenson calls this freeze-thaw approach to trials, that some people who don't do trials seem to have, which is that you get your patients all at once and that you can just randomize them all at the same time. But in reality, for those of you who work in clinics, that That's almost never the case because patients, when they appear for a trial, they expect to be treated then and there. They're not going to be in a position to wait for all the rest of the recruitment to finish, then have people be randomized, then have people receive the treatment that they're randomized to. So this is a very important practical constraint, which kind of also points to the fact that when we're doing clinical trials, we're running them in clinics and usually in working places. They're going to have to deal with those constraints. So when people start talking about re-randomizing patients to get a more favorable allocation with respect to covariate imbalances or whatever, it's a non-starter. So we have to be able to randomize patients as they appear to the trial in real time, in a sequential way is probably the most important thing to always keep in mind. There are a number of steps and things we have to think about once we've decided what kind of a randomization we're going to do. We have to generate the randomization lists. We actually have to have this way of receiving the allocation, and that maintains allocation concealment. And we also have to think about how to unblind and then concerns for reporting the study protocol. So generally, generation of the randomization list falls on the statistician or an independent statistician. So you as the researcher, you'll work with your statistician and you'll design the randomization the way we've discussed earlier on in this talk. And then you'll have the list generated by an independent person, and they can use any number of statistical software packages to do that. Importantly, when people talk about the methods of randomization, sometimes people get really caught up in how the random numbers are actually generated. Well, in 2019, we're not really concerned about that. We're letting the computer do it, and there are validated ways of doing that, and that's it. Once upon a time, you had to get a big giant book and pick a random page and pick a random column and pick a random row, and there was your number. We now have computer algorithms that create random numbers for us that are more than suitable for our purposes. So worrying about how the random allocation itself was generated is kind of a trivial point. These are the important things. And importantly, that list and how it's generated has to be replicable. So this is a bit of code that I would use with R to create a randomization list. And I've got important information here that I could recreate the exact same randomization list I've given you just by rerunning the code. And again, I talked about this when we said something about minimization. We have kind of programming concerns, which is if we have adaptive strategies, then we can't just create a list at the beginning. And by a list, I mean a spreadsheet with a list of allocations in order of how they come next. And so you have to have some kind of a programming setup or a computer setup where you can do this in real time like we discussed before. Emergency unblinding can be a very important thing, can be one of the most critical things about a trial, depending on what kind of treatment and what the risk profile is for the patients enrolled. And so there will be situations where you need to know very quickly what treatment a particular patient got because they had a severe adverse event. And so when we set up the randomization list, usually what you have is a version of it that's available to a couple of people who are nominated that they can be contacted at any point, and they can look at the allocation list immediately and tell you, yes, patient number 163, they received the active treatment. We have other things where you can tear off labels of treatments and you can see what was underneath. You can have an external service who does that. But everything about the emergency unblinding has to be in place before the trial starts because it's a patient safety issue. It has to be fully transparent, documented. And you have to also have systems and think in advance for how and if you're going to notify patients and what it means for the continuation of the trial. So, what's it going to take to stop the trial? And you need to know all that before you start the trial if that's not obvious. This should go into the study protocol. Again, which needs to be designed. It must be designed before enrollment begins. How you did the randomization, how you did the allocation concealment, how the treatment codes will be computed. If you're working with a manufacturer, then you're going to need them to provide you with blinded treatments and how that's going to be done and communicated. And similarly, everything has to be reported in consort, right? So And Consort requires this information. And if you're going to publish a clinical trial, you have to follow Consort guidelines now. And so you're going to have to talk about, the method used to generate the random allocation sequence. And again, you'd work with your statistician to write all this information up. And so I would just talk about the software I used, the type of randomization. Did I use a complete randomization? Did I use blocks? What are the block sizes and so on? How did I describe my allocation concealment? Am I stuffing foil into envelopes, or do I have an electronic database set up? And again, this is the part where you want to demonstrate to other people who don't know you and don't have any necessarily a reason to trust you or not trust you. You want to describe the system that was a foolproof way of maintaining allocation concealment, and then how everything was implemented. So the independent statistician generated a allocation sequence. It was communicated to the maintainer of the electronic database, and so on and so forth. Who was enrolling participants and screening them? Who actually kind of clicks the button to get the randomization, and so on. So all that information has to be understood so it can be reported in Consort. And again, obviously this stuff has to be done before the trial starts. So you can't wait until it's time to report the trial, because you can't make this stuff up after the fact. All right, so that's our talk on randomization. As ever, if you have additional questions, please get on the discussion board and leave one underneath the appropriate question and answer section. If you want to email me, you can feel free, and I can anonymize your question and then put the answer up. Or if you have any other questions, you just feel free to get in touch however you want to get in touch. All right. Thank you very much.